Hello students, welcome to lecture video classes, 2nd PUC Chemistry, organized by Mysuru District PU Chemistry Lecturers Forum. This is Dr. Venkatesh PK. You are watching my PU Chemistry YouTube channel. Kindly subscribe to our channel and keep watching, and also press the bell icon so that you keep yourself updated regularly. Okay? As we all know, in our previous classes, previous videos, we have discussed about various units of concentration. Alva? Namma hindina classಗಳಲ್ಲಿ ಹಿಂದಿನ ವಿಡಿಯೋಸ್ಗಳಲ್ಲಿ ನಾವು ಯೂನಿಟ್ಸ್ ಆಫ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಯಾವುದೆಲ್ಲ ಥರ ನಾವು ಕಾನ್ಸಂಟ್ರೇಷನ್ಗಳನ್ನು ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡಬಹುದು ಅಂತನ್ನೋದನ್ನು ನಾವು ವಿ ಹ್ಯಾವ್ ಅಂಡರ್ಸ್ಟುಡ್. ಅದರ ಜೊತೆಗೆ ವಿ ಹ್ಯಾವ್ ಆಲ್ಸೋ ಸಾಲ್ವ್ಡ್ ಸರ್ಟೆನ್ ನ್ಯೂಮರಿಕಲ್ ಪ್ರಾಬ್ಲಮ್ಸ್. ಓಕೆ, ಈಗ ಇನ್ನು ಮುಂದೆ ಯಾವುದೆಲ್ಲ ಸೊಲ್ಯೂಷನ್ಸು ಪಾಸಿಬಲ್ ಇದೆ, ಅಂದರೆ ಯಾವುದೆಲ್ಲ ಸೊಲ್ಯೂಟು ಯಾವುದೆಲ್ಲ ಸಾಲ್ವೆಂಟಲ್ಲಿ ಡಿಸಾಲ್ವ್ ಆಗಿ ಸೊಲ್ಯೂಷನ್ಸ್ ಫಾರ್ಮ್ ಮಾಡುತ್ತೆ. ಎಲ್ಲ ಸೊಲ್ಯೂಟು ಎಲ್ಲ ಸಾಲ್ವೆಂಟಲ್ಲೂ ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಮಾಡುತ್ತಾ? ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ವಾಟರ್ ಒಳಗಡೆ ಇಫ್ ಯು ಆ್ಯಡ್ ಸೊಲ್ಯೂಟ್ಸ್ ಸಚ್ ಆಸ್ ಗ್ಲೂಕೋಸ್, ಇಫ್ ಯು ಆ್ಯಡ್ ಸೊಲ್ಯೂಟ್ಸ್ ಸಚ್ ಆಸ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್, ಪೊಟ್ಯಾಷಿಯಂ ಕ್ಲೋರೈಡ್ ಆರ್ ಯೂರಿಯಾ ಎಕ್ಸೆಟ್ರಾ, ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆಗುತ್ತೆ. ಅದೇ ವಾಟರ್ ಒಳಗಡೆ ನೀವು ಒಂದು ಸ್ವಲ್ಪ ಆಯಿಲ್ ಹಾಕಿಬಿಡಿ, ಇಟ್ ಕುಡ್ ಬಿ ಎನಿ ಕೋಕೋನಟ್ ಆಯಿಲ್ ಆರ್ ಗ್ರೌಂಡ್ನಟ್ ಆಯಿಲ್ ಆರ್ ಎನಿಥಿಂಗ್, ಸ್ವಲ್ಪ ಆಯಿಲ್ ಹಾಕಿಬಿಡಿ, ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆಗುತ್ತಾ? ಫಾರ್ಮ್ ಆಗಲ್ಲ. ಸೊ ನಮಗೆ ಇದರಿಂದ ಏನು ಗೊತ್ತಾಗುತ್ತೆ? ಆಲ್ ದಿ ಕಾಂಬಿನೇಷನ್ ಆಫ್ ಸೊಲ್ಯೂಟ್ ಆ್ಯಂಡ್ ಸಾಲ್ವೆಂಟ್, ಕಾಂಬಿನೇಷನ್ ಆಫ್ ಆಲ್ ದ ಸಬ್ಸ್ಟೆನ್ಸಸ್ ಕೆನಾಟ್ ಲೀಡ್ ಟು ಫಾರ್ಮೇಷನ್ ಆಫ್ ಸೊಲ್ಯೂಷನ್ಸ್. ಹಾಗಾದರೆ ಯಾವುದೆಲ್ಲ ಸಬ್ಸ್ಟೆನ್ಸ್ಗಳು ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಮಾಡುತ್ತೆ? ಒಂದು. ಎರಡನೇ ಪ್ರಶ್ನೆ, ಎಷ್ಟು ಆ್ಯಡ್ ಮಾಡಬಹುದು? ಈಗ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್, ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ನ ನಾವು ಸ್ವಲ್ಪ ಡಿಸಾಲ್ವ್ ಮಾಡ್ತೀವಿ, ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆಗುತ್ತೆ, ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಡಿಸಾಲ್ವ್ ಮಾಡ್ತೀವಿ, ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆಗುತ್ತೆ. ಈ ಥರ ಎಷ್ಟು ಕ್ವಾಂಟಿಟಿ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ನ ಡಿಸಾಲ್ವ್ ಮಾಡಬಹುದು? ಅದನ್ನೇನಾದರೂ ವ್ಯತ್ಯಾಸ ಮಾಡಬಹುದಾ? ಜಾಸ್ತಿ ಮಾಡಬಹುದಾ? ಕಮ್ಮಿ ಮಾಡಬಹುದಾ? ಸೊ ಈ ಎಲ್ಲ ಪ್ರಶ್ನೆಗಳಿಗೆ ನಾವು ಉತ್ತರ ಪರ್ಹ್ಯಾಪ್ಸ್ ದಿಸ್ ವಿಡಿಯೋ ಕ್ಲಾಸ್, ಮೇ ಬಿ ಇನ್ ದ ನೆಕ್ಸ್ಟ್ ವಿಡಿಯೋ ಕ್ಲಾಸ್ ಆಲ್ಸೋ we will try and find out answers for all such kind of questions. So for that we have to understand what is known as solubility. We have to understand the concept of solubility. Okay? Solubility ಅಂದರೆ ಏನು ಅಂತ ಅನ್ನೋದನ್ನು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳೋದಕ್ಕಿಂತ ಮುಂಚೆ ನಾವು we will consider a certain situation. Say for example, this is certain amount of a solvent such as say 1 liter water. Let us assume ಇದು 1 liter water ಇದೆ. ಇದರೊಳಗಡೆ ನಾನು ಯಾವುದೋ ಒಂದು ವಾಟರ್ ಸಾಲ್ಯುಬಲ್ ಸೊಲ್ಯೂಟ್ನೇ ಆ್ಯಡ್ ಮಾಡ್ತೀನಿ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಅಂತ ಅಂದ್ಕೊಳ್ಳಿ. ಎಷ್ಟು ಆ್ಯಡ್ ಮಾಡ್ತೀನಿ? ಸ್ವಲ್ಪ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಆ್ಯಡ್ ಮಾಡ್ತೀನಿ. ಐ ವಿಲ್ ಸ್ಟರ್ ಇಟ್ ಥರೋಲಿ, ಚೆನ್ನಾಗಿ ಸ್ಟಿರ್ ಮಾಡ್ತೀನಿ. ಸೊ ಸ್ಟಿರ್ ಮಾಡಿದಾಗ ಏನಾಯಿತು? ನನಗೆ ಸೊಲ್ಯೂಷನ್ ಸಿಕ್ತು. ಆಫ್ಟರ್ ದ್ಯಾಟ್ ಐ ವಿಲ್ ಆ್ಯಡ್ ಸಮ್ ಮೋರ್ ಅಮೌಂಟ್ ಆಫ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್, ಸ್ಟಿರ್ ಇಟ್, ಸ್ಟಿಲ್ ದೇರ್ ಇಸ್ ಸೊಲ್ಯೂಷನ್. ಐ ವಿಲ್ ಆ್ಯಡ್ ಸಮ್ ಮೋರ್ ಅಮೌಂಟ್. ನಾನು ಜಾಸ್ತಿ ಸೊಲ್ಯೂಟ್ ಕಾನ್ಸಂಟ್ರೇಷನ್ನ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತಾ ಹೋಗ್ತೀನಿ. ಐ ವಿಲ್ ಗೋ ಆನ್ ಆ್ಯಡಿಂಗ್ ಮೋರ್ ಆ್ಯಂಡ್ ಮೋರ್ ಆ್ಯಂಡ್ ಮೋರ್ ಅಮೌಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಟ್. ಏನಾಗ್ತಾ ಹೋಗುತ್ತೆ? ನಾನು ಸೊಲ್ಯೂಟ್ ಆ್ಯಡ್ ಮಾಡ್ದಂಗೆಲ್ಲ ಡಿಸಾಲ್ವ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ಈ ಪ್ರಾಸೆಸ್ಗೆ ನಾವೇನಂತ ಕರಿತೀವಿ? ಡಿಸೊಲ್ಯೂಷನ್ ಅಂತ ಕರಿತೀವಿ. ಡಿಸೊಲ್ಯೂಷನ್ ಅಂತ ಕರಿತೀವಿ ಅಲ್ವಾ? ಆಲ್ ಆಫ್ us might surely have experienced this kind of situation ಅಲ್ವಾ? ಒಂದು ಸೊಲ್ಯೂಟ್ಗೆ, ಐ ಮೀನ್ ಒಂದು ಸಾಲ್ವೆಂಟ್ಗೆ, ಸ್ಪೆಸಿಫೈಡ್ ಅಮೌಂಟ್ ಆಫ್ ಸಾಲ್ವೆಂಟ್ಗೆ ಸೊಲ್ಯೂಟ್ ಆ್ಯಡ್ ಮಾಡ್ತಾ ಹೋದರೆ ಡಿಸಾಲ್ವ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಎಲ್ಲಿ ತನಕ ಡಿಸಾಲ್ವ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ? ಕ್ಯಾನ್ ವಿ ಆ್ಯಡ್ ಇನ್ಫೈನೈಟ್ ಅಮೌಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಟ್? ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಹಾಕ್ತಾನೇ ಇರಬಹುದಾ ಸ್ಪೆಸಿಫೈಡ್ ಕ್ವಾಂಟಿಟಿ ಆಫ್ ಸಾಲ್ವೆಂಟ್ಗೆ? ಡೆಫಿನೆಟ್ಲಿ ನೋ. ಒಂದು ಸ್ಟೇಜ್ ತನಕ, ಒಂದು ಲೆವೆಲ್ ತನಕ ಡಿಸಾಲ್ವ್ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಓಕೆ, ಆ್ಯಸ್ ವಿ ಗೋ ಆನ್ ಆ್ಯಡಿಂಗ್ ಸೊಲ್ಯೂಟ್, ದ ಸೊಲ್ಯೂಟ್ ಗೋಸ್ ಆನ್ ಗೆಟಿಂಗ್ ಡಿಸಾಲ್ವ್ಡ್ ಇನ್ ಸಾಲ್ವೆಂಟ್, ಬಟ್ ನಾಟ್ ಇನ್ಫೈನೈಟ್ಲಿ. ದಿ ಡಿಸೊಲ್ಯೂಷನ್ ಟೇಕ್ಸ್ ಪ್ಲೇಸ್ ಓನ್ಲಿ ಅಪ್ ಟು ಸರ್ಟನ್ ಎಕ್ಸ್ಟೆಂಟ್. ಅದಾದಮೇಲೆ very small amount of solute also ಕಮ್ಸ್ ಆ್ಯಂಡ್ ಗೆಟ್ಸ್ ಸೆಟಲ್ಡ್ ಎಟ್ ದಿ ಬಾಟಮ್, ಅಂದರೆ ಡಿಸಾಲ್ವ್ ಆಗಲ್ಲ. ಸೊ ಈ ಪ್ರಾಸೆಸ್ನ ನಾವೇನಂತ ಕರಿತೀವಿ? ಕ್ರಿಸ್ಟಲೈಸೇಷನ್ ಅಂತ ಕರಿತೀವಿ. ಕ್ರಿಸ್ಟಲೈಸೇಷನ್ ಅಂತ ಕರಿತೀವಿ. ಓಕೆ, ನಾವು ಈಗ ಎರಡು ಪ್ರಾಸೆಸ್ ಇದೆ ನಮ್ಮ ಹತ್ರ. ಒಂದು ಡಿಸಲ್ಯೂಷನ್, ಎರಡನೇದು ಕ್ರಿಸ್ಟಲೈಸೇಷನ್. ಇದೆರಡು ಪರಸ್ಪರ ವಿರುದ್ಧವಾದ ಪ್ರಾಸೆಸ್ಗಳು, ಪರಸ್ಪರ ವಿರುದ್ಧವಾದ ಪ್ರಕ್ರಿಯೆಗಳು. ಕರೆಕ್ಟಾ? ಸೊ ಇಫ್ ಡಿಸಲ್ಯೂಷನ್ ಈಸ್ ಕನ್ಸಿಡರ್ಡ್ ಟು ಬಿ ಎ ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್, ದೆನ್ ಕ್ರಿಸ್ಟಲೈಸೇಷನ್ ಈಸ್ ಎ ರಿವರ್ಸ್ ರಿಯಾಕ್ಷನ್. ಯಾಕೆ ಅಂತ ಕೇಳಿದ್ರೆ, ಡಿಸಲ್ಯೂಷನ್ನಲ್ಲಿ ಏನಿದೆ, ಸೊಲ್ಯೂಟ್ ಪಾರ್ಟಿಕಲ್ಸ್ ತಮ್ಮ ಫೇಸನ್ನು ಬಿಟ್ಟು ಸೊಲ್ಯೂಷನ್ ಫೇಸ್ಗೆ ಎಂಟರ್ ಆಗ್ತಾ ಇದೆ, ಸಾಲ್ವೆಂಟ್ ಫೇಸ್ಗೆ ಎಂಟರ್ ಆಗ್ತಾ ಇದೆ ಅಲ್ವಾ? ಸೊ ಇನ್ ಡಿಸಲ್ಯೂಷನ್ ವಾಟ್ ಈಸ್ ಹ್ಯಾಪನಿಂಗ್? ಇಲ್ಲಿ ಸೊಲ್ಯೂಟ್ ಯಾವುದು? ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್. ಸೊಲ್ಯೂಟ್ ಯಾವುದು? ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್. ಆ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಯಾವ ಫೇಸ್ನಲ್ಲಿದೆ? ಸಾಲಿಡ್ ಫೇಸ್ನಲ್ಲಿ ಇದೆ. ಸೊ ಡಿಸಾಲ್ವ್ ಆದಮೇಲೆ ದಟ್ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಈಸ್ ಗಿವಿಂಗ್ ಅಪ್ ಇಟ್ಸ್ ಫೇಸ್. ಆ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡು ತನ್ನ ಸಾಲಿಡ್ ಫೇಸನ್ನು ಬಿಟ್ಟು ತ್ಯಜಿಸಿ ಸೊಲ್ಯೂಷನ್ ಫೇಸ್ಗೆ, ಅಂದರೆ ಲಿಕ್ವಿಡ್ ಫೇಸ್ಗೆ, ಇಲ್ಲಿ ಸಾಲ್ವೆಂಟ್ ಲಿಕ್ವಿಡ್ ಆಗಿರೋದ್ರಿಂದ ಸೊಲ್ಯೂಷನ್ಗೂ ಕೂಡ ಲಿಕ್ವಿಡ್ ಫೇಸ್ ಇರುತ್ತೆ. ಸೊ ಅದು ಸೊಲ್ಯೂಟು ಸಾಲಿಡ್ ಫೇಸ್ನ ಬಿಟ್ಟು ಆ ಸೊಲ್ಯೂಟು ಸೊಲ್ಯೂಷನ್ ಫೇಸ್ಗೆ, ಅಂದರೆ ಲಿಕ್ವಿಡ್ ಫೇಸ್ಗೆ ಎಂಟರ್ ಆಗ್ತಾ ಇದೆ ಅಲ್ವಾ? ಸೊಲ್ಯೂಟ್ ಈಸ್ ಎಂಟರಿಂಗ್ ಇನ್ ಟು ಲಿಕ್ವಿಡ್ ಫೇಸ್. ದಿಸ್ ಈಸ್ ಡಿಸಲ್ಯೂಷನ್. ಓಕೆ, ಕ್ರಿಸ್ಟಲೈಸೇಷನಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ? ದಟ್ ಮೀನ್ಸ್ we have added the maximum amount of solute, a very small extra amount. That extra amount is getting crystallized. That means solute is coming from solution phase back into its original phase. Alva? So solution phase nalli iddantaha solute, liquid phase nalli iddantaha solute ವಾಪಸ್ ಸಾಲಿಡ್ ಫೇಸ್ಗೆ ರಿಟರ್ನ್ ಆಗ್ತಾ ಇದೆ. ಸೊ ಹಾಗಿರೋದ್ರಿಂದ these two are mutually opposite processes. Is that right? Now, when dissolution process and crystallization process are taking place at same rates, okay, we say that the system is at equilibrium. Alva? What is actually the meaning of equilibrium? Equilibrium means there are two processes. Those two processes are mutually opposite in direction. Both are taking place at same rates. When the rate of forward reaction becomes equal to the rate of reverse reaction, we say the system has attained equilibrium. So, equilibrium reach ಆದಾಗ ನಮ್ಮ solution, ನಮ್ಮ system, we call it as saturated solution. Saturated solution. So saturated solution ಅಂದ್ರೆ ಏನು? Saturated solution ನಲ್ಲಿ the process of dissolution and the process of crystallization are at equilibrium. That is, maximum amount of solute has been already dissolved in the solvent. No more solute can be dissolved in the solvent. So ಆ situation ನಾವು reach ಆದಾಗ we say we have a saturated solution. So saturated solution ಅಂತಂದ್ರೆ ಏನು? A solution in which maximum amount of solute has already been dissolved. A solute in which maximum amount of solute is being dissolved is called a saturated solution. So ನಾವಿಲ್ಲಿ ಇನ್ನು ಒಂದು ಹೇಳ್ಬೋದು unsaturated solution ಅಂತ. Unsaturated solution. Unsaturated solution ಅಂತಂದ್ರೆ a solution that has not reached saturation yet. ಅಲ್ವಾ? A solution in which some more amount of solute can still be dissolved at a particular temperature is called unsaturated solution. ಸೊ ಈ ಟೆಂಪ್ರೇಚರ್ ಅನ್ನೋ ಟರ್ಮ್ ತುಂಬ ಇಂಪಾರ್ಟೆಂಟು. ಆ ಡೆಫಿನಿಷನ್ನಲ್ಲಿ ನಾವು ಇನ್ಕ್ಲೂಡ್ ಮಾಡ್ಕೋಬೇಕಾಗತ್ತೆ, ಬೋತ್ ಸ್ಯಾಚುರೇಟೆಡ್ ಆ್ಯಂಡ್ ಅನ್ಸ್ಯಾಚುರೇಟೆಡ್. ಸೊ ಸ್ಯಾಚುರೇಟೆಡ್ ಸೊಲ್ಯೂಷನ್ ಅಂದರೆ ಏನು? ಇಟ್ ಈಸ್ ಎ ಸೊಲ್ಯೂಷನ್ ಇನ್ ವಿಚ್ ಮ್ಯಾಕ್ಸಿಮಮ್ ಅಮೌಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಟ್ ಹ್ಯಾಸ್ ಬೀನ್ ಡಿಸಾಲ್ವ್ಡ್ at a particular temperature is called saturated solution. Any small amount of extra solute added will not get dissolved, but it gets crystallized. It gets settled at the bottom of the solution. Okay? Then unsaturated ಅಂದರೂ ಕೂಡ ನಾವು ಅದೇ ಡೆಫಿನಿಷನ್ ಹೇಳ್ತೀವಿ, ಅದೇ ಥರ ಡೆಫಿನಿಷನ್ ಹೇಳ್ತೀವಿ. ಏನಂತ ಹೇಳ್ತೀವಿ? ಎ ಸೊಲ್ಯೂಷನ್ ಫಾರ್ ವಿಚ್ ಸಮ್ ಮೋರ್ ಅಮೌಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಟ್ ಕ್ಯಾನ್ ಬಿ ಡಿಸಾಲ್ವ್ಡ್ at a particular temperature is called unsaturated solution. Okay. Now, ಈ ಸಿಚುವೇಷನ್ನಲ್ಲಿ the amount of solute dissolved, ಯಾವ ಸಿಚುವೇಷನಲ್ಲಿ? ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಬಂದಾಗ. ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಬಂದಾಗ ಅಂದರೂ ಒಂದೇ, ಸ್ಯಾಚುರೇಟೆಡ್ ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆದಾಗ ಅಂತಂದರೂ ಒಂದೇ. ಸೊ ಈಕ್ವಿಲಿಬ್ರಿಯಂ ಬಂದಾಗ, ಸ್ಯಾಚುರೇಟೆಡ್ ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆದಾಗ, ದ ಅಮೌಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಟ್ ವಾಟ್ ಈಸ್ ಡಿಸಾಲ್ವ್ಡ್, ದ ಮ್ಯಾಕ್ಸಿಮಮ್ ಅಮೌಂಟ್ ಆಫ್ ಸೊಲ್ಯೂಟ್ ದಟ್ ಈಸ್ ಡಿಸಾಲ್ವ್ಡ್, that is called solubility. So ಅಲ್ಲಿಗೆ solubility ಅಂತಂದರೆ ಏನಾಯಿತು? We can define solubility in this way. Solubility is the maximum amount of solute. Solubility is the maximum amount of solute that can be dissolved in a specified amount of solvent at a particular temperature is called solubility. Solubility is the maximum amount of solute that can be dissolved in a specified amount of solvent at a particular temperature is known as solubility. Okay? ಈ ಸಾಲಿಬಿಲಿಟಿನ ನಾವು ಬೇರೆ ಬೇರೆ ಯೂನಿಟ್ಸಲ್ಲಿ ಎಕ್ಸ್ಪ್ರೆಸ್ ಮಾಡಬಹುದು. ಇನ್ ಸರ್ಟನ್ ಸಿಚುವೇಷನ್ಸ್ ವಿ ಎಕ್ಸ್ಪ್ರೆಸ್ ಇಟ್ ಇನ್ ಮಾಸ್ ಪರ್ಸೆಂಟೇಜ್, ಇನ್ ಸರ್ಟನ್ ಅದರ್ ಸಿಚುವೇಷನ್ ವಿ ಕ್ಯಾನ್ ಯೂಸ್ ಮೋಲ್ ಫ್ರ್ಯಾಕ್ಷನ್ ಎಕ್ಸೆಟ್ರಾ. ಓಕೆ, ಈಗ ಈ ಸಾಲಿಬಿಲಿಟಿ ಅಂತನ್ನೋದು ಯಾವುದೆಲ್ಲ ಫ್ಯಾಕ್ಟರ್ಸ್ ಮೇಲೆ ಡಿಪೆಂಡ್ ಆಗಿದೆ? ಓಕೆ, ಎಲ್ಲ ಸೊಲ್ಯೂಟು ಎಲ್ಲ ಸಾಲ್ವೆಂಟಲ್ಲಿ ಡಿಸಾಲ್ವ್ ಆಗುತ್ತಾ? ಆಲ್ರೆಡಿ ನಾವು ವಿಚಾರ ಮಾಡಿದ ಹಾಗೆ ಉತ್ತರ ಇಲ್ಲ. ಓಕೆ, ಉತ್ತರ ಇಲ್ಲ ಅಂತ ಅಂದರೆ ನಾವು ಎಲ್ಲ ಸೊಲ್ಯೂಟು ಎಲ್ಲ ಸಾಲ್ವೆಂಟಲ್ಲಿ ಡಿಸಾಲ್ವ್ ಆಗಲ್ಲ. ಕೆಲವು ಸೊಲ್ಯೂಟ್ ಮಾತ್ರ ಕೆಲವೇ ಸಾಲ್ವೆಂಟಲ್ಲಿ ಡಿಸಾಲ್ವ್ ಆಗುತ್ತೆ. ಈಗ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ವಾಟರ್ನ ನಾವು ಯೂನಿವರ್ಸಲ್ ಸಾಲ್ವೆಂಟ್ ಅಂತ ಕರಿತೀವಿ. ಯೂನಿವರ್ಸಲ್ ಸಾಲ್ವೆಂಟ್ ಅನ್ನೋ ಮಾತಿಗೆ ಏನರ್ಥ? ವಾಟ್ರಲ್ಲಿ ಎಲ್ಲ ಸೊಲ್ಯೂಟ್ಗಳು ಡಿಸಾಲ್ವ್ ಆಗುತ್ತೆ ಅಂತ ಅರ್ಥನಾ? ಅಲ್ಲ. ವಾಟರ್ ಹ್ಯಾಸ್ ಎಬಿಲಿಟಿ ಟು ಡಿಸಾಲ್ವ್ ಮೋರ್ ನಂಬರ್ ಆಫ್, ಮ್ಯಾಕ್ಸಿಮಮ್ ನಂಬರ್ ಆಫ್ ಸೊಲ್ಯೂಟ್ಸ್. ಅದಕ್ಕೋಸ್ಕರ ಯೂನಿವರ್ಸಲ್ ಸಾಲ್ವೆಂಟ್ ಅಂತ ಹೇಳ್ತೀವಿ ಹೊರತು ನಾಟ್ ದಟ್ ವಾಟರ್ ಕ್ಯಾನ್ ಡಿಸಾಲ್ವ್ ಈಚ್ ಆ್ಯಂಡ್ ಎವ್ರಿ ಸೊಲ್ಯೂಟ್. ಓಕೆ, ನಾವು ಈಗ ಯಾವುದೆಲ್ಲ ಅಂಶಗಳ ಮೇಲೆ ಈ ಸಾಲಿಬಿಲಿಟಿ ಅಂತ ಅನ್ನೋದು ಡಿಪೆಂಡ್ ಆಗಿದೆ, ಅದನ್ನು ಏನಾದರೂ ನಾವು ಆಲ್ಟರ್ ಮಾಡಬಹುದಾ? ಆ ಸಾಲಿಬಿಲಿಟಿನ ಏನಾದರೂ ನಾವು ವ್ಯತ್ಯಾಸ ಮಾಡ್ಬೋದಾ, ಜಾಸ್ತಿ ಮಾಡ್ಬೋದಾ, ಕಮ್ಮಿ ಮಾಡ್ಬೋದಾ? ಯಾವುದೆಲ್ಲ ಫ್ಯಾಕ್ಟರ್ಗಳ ಮೇಲೆ ಈ ಚೇಂಜ್ ಇನ್ ಸಾಲಿಬಿಲಿಟಿ ಅಂತ ಅನ್ನೋದು ಡಿಪೆಂಡ್ ಆಗುತ್ತೆ ಅಂತೆಲ್ಲ ಅಂಶಗಳನ್ನು ನಾವು ಈ ಕ್ಲಾಸ್ನಲ್ಲಿ ನಾವು ವಿ ವಿಲ್ ಡಿಸ್ಕಸ್ ಒನ್ ಬೈ ಒನ್. ಓಕೆ, ನೌ ಲೆಟ್ ಅಸ್ ಕನ್ಸಿಡರ್ solutions in liquid phase. Okay, the most of our discussion in the rest of the chapter will be restricted to, will be confined to solutions in liquid phase. Liquid phase ಅಂದರೆ ಸಾಲ್ವೆಂಟ್ ಲಿಕ್ವಿಡ್ ಆಗಿರುತ್ತೆ. ನಾವು ನಮ್ಮ the very first video we discussed different types of solutions. ಅದರಲ್ಲಿ solutions in liquid phase ಅದನ್ನು ನಾವು ಕಲ್ತಿದ್ವಿ. ಅಂದರೆ ಅಲ್ಲಿ ಸಾಲ್ವೆಂಟ್ ಏನಾಗಿರುತ್ತೆ? ಲಿಕ್ವಿಡ್ ಆಗಿರುತ್ತೆ. ನೌ ಲೆಟ್ ಅಸ್ ಕನ್ಸಿಡರ್ ಎ ಸೊಲ್ಯೂಷನ್ ಆಫ್ ಸಾಲಿಡ್ ಇನ್ ಲಿಕ್ವಿಡ್. ಎ ಸೊಲ್ಯೂಷನ್ ಆಫ್ ಸಾಲಿಡ್ ಇನ್ ಲಿಕ್ವಿಡ್. ಸಾಲಿಡ್ ಇನ್ ಲಿಕ್ವಿಡ್ ಅಂತಂದರೆ ಸೊಲ್ಯೂಟು ಸಾಲಿಡ್ ಆಗಿರುತ್ತೆ, ಸಾಲ್ವೆಂಟು ಲಿಕ್ವಿಡ್ ಆಗಿರುತ್ತೆ. ಸೊಲ್ಯೂಟ್ ವಿಲ್ ಬಿ ಸಾಲಿಡ್, solvent will be liquid. Okay, now let us consider such a solutions. Now what are the factors that determine solubility in a solid in liquid type of solution? Factors on which, factors that determine solubility. ಯಾವುದರಲ್ಲಿ? In a solid, in liquid kind of solution. For example, salt solution, sugar solution, etc. Okay. The very first factor is nature of solute. Nature of solute and solvent, of course. Nature of solute. ಈಗ ನೋಡಿ, ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ನಾನು ಆಗಲೇ ಹೇಳಿದ ಹಾಗೆ, ಕನ್ಸಿಡರ್ ಟೂ ಸಿಚುವೇಶನ್ಸ್. This is say around 100 ml water. This is say around 100 ml water. In this add solutes such as sodium chloride, potassium chloride. Dissolve ಮಾಡಿ. Dissolve ಆಗುತ್ತಾ? Definitely dissolve ಆಗುತ್ತೆ. ಅದು ನಮಗೆ it is we all are very familiar about this. ಕರೆಕ್ಟಾ? ಸೊ ಅದೇ ಈ ಕಡೆ ಏನು ಮಾಡಿ, you add substance such as camphor. Add substance such as camphor ಅಂದರೆ ಕರ್ಪೂರ. ಕರ್ಪೂರನ ಪುಡಿ ಮಾಡಿಬಿಟ್ಟು ನೀರು ಒಳಗಡೆ ಹಾಕಿ. ಸೊಲ್ಯೂಷನ್ ಫಾರ್ಮ್ ಆಗುತ್ತಾ? ಆಗಲ್ಲ. ಕರ್ಪೂರದ್ದು ಪೌಡರ್ ಎಲ್ಲ, ಐ ಮೀನ್ ದಿ ಕ್ರಿಸ್ಟಲ್ಸ್ ದಟ್ ದೇ ವಿಲ್ ಬಿ ಫ್ಲೋಟಿಂಗ್. ಕರ್ಪೂರದ್ದು ಪೌಡರ್ ಎಲ್ಲ ವಾಟರ್ ಮೇಲೆ ತೇಲ್ತಾ ಇರುತ್ತೆ ಅಲ್ವಾ? ಸೊ ಸಪೋಸ್ ಟೇಕ್ 100 ml of instead of water, take solvents such as camphor gets dissolved in, okay, it gets dissolved in solvents such as chloroform, carbon tetrachloride, benzene, etc. So ಇದು ನೋಡಿದರೆ ನಮಗೇನು ಗೊತ್ತಾಗುತ್ತೆ? So we can understand that like dissolve in like. Like dissolve in like. ಏನು ಹಾಗಂದರೆ ಅಂತ ಕೇಳಿದ್ರೆ, ಈ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್, ಪೊಟ್ಯಾಷಿಯಂ ಕ್ಲೋರೈಡ್ ಇದೆಲ್ಲ ಇದೆಯಲ್ಲ, ದೀಸ್ ಆರ್ polar compounds. They are ionic. Alva? They are ionic. That means they have ions which have charges. Okay. Then water is also polar. Water is also polar. Yake? Water molecule nalli, because of difference in electronegativities between oxygen and hydrogen, more the electron cloud is concentrated on oxygen molecule, giving it a partial negative charge. As a result, the hydrogen atom gets partial positive charge. Correct? So therefore there is polarity. That means there is charge separation in the molecule. So because of this, this can interact with the solute. ಏನಾಗುತ್ತೆ, ನಾವು ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ನ ವಾಟರಲ್ಲಿ ಹಾಕಿದಾಗ it gets ionized. So sodium ions are attracted by oxygen atoms which have partial negative charge. Okay, these have partial negative charge. Since sodium ion has positive charge, it is attracted by the water molecules which has a partial negative charge on oxygen atom. Similarly, what happens to chlorine? Chlorine atom is attracted by hydrogen atoms. Chlorine atom is attracted by hydrogen atoms which have partial positive charge. On the other hand, chlorine has partial negative charge. So this is what we mean by dissolution. That means there is a kind of interaction. There is a kind of interaction between whom? Between the solute and solvent particles. ನೀವು ಕ್ಯಾಂಫರ್ ಅಂತ ಸಬ್ಸ್ಟೆನ್ಸ್ ತೊಗೊಂಡು ವಾಟರ್ ಒಳಗಡೆ ಹಾಕಿದರೆ, ಆಯಿಲ್ ತೊಗೊಂಡು ಯಾವುದೋ ಒಂದು ಲಿಪಿಡ್ ತೊಗೊಂಡು ಅಥವಾ ಯಾವುದೋ ಒಂದು ಫ್ಯಾಟಿ ಆಸಿಡ್ ತೊಗೊಂಡು ವಾಟರ್ ಒಳಗಡೆ ಹಾಕಿದರೆ, ದೇರ್ ಈಸ್ ನೋ ಇಂಟರಾಕ್ಷನ್ ಎಟ್ ಆಲ್. ದೇರ್ ಫಾರ್ ಡಿಸಲ್ಯೂಷನ್ ಡಸ್ ನಾಟ್ ಟೇಕ್ ಪ್ಲೇಸ್. ಕ್ಯಾಂಫರ್ ತೊಗೊಂಡೋಗಿ ಆರ್ಗ್ಯಾನಿಕ್ ಸಾಲ್ವೆಂಟಲ್ಲಿ ಹಾಕಿದ್ರೆ ದೇರ್ ಇಸ್ ಅಗೇನ್ ಇಂಟರಾಕ್ಷನ್. ದೇ ಆರ್ ಬೋತ್ ಆರ್ ನಾನ್ ಪೋಲಾರ್, ಬಟ್ there is interaction such as hydrophobic interaction etc. Okay, so ಆ interaction ಇರೋದ್ರಿಂದ solubility possible ಆಗುತ್ತೆ. So that is why we say like dissolve in like. Okay, and for example camphor in carbon tetrachloride or chloroform or any other organic solvent. Sarina? Now this is the first factor, that is nature of solute. Now coming to the next factor that determines the solubility. Next factor on which solubility is dependent. Next factor is temperature. Temperature. Again for this also let us consider two different situations. Okay. In first situation, I will add say for 100 ml of water, I will add a salt such as potassium nitrate. A salt such as potassium nitrate. ನೀವು ಒಂದು ಬೀಕರಲ್ಲಿ ವಾಟರ್ ತಗೊಂಡು ಪೊಟ್ಯಾಷಿಯಂ ನೈಟ್ರೇಟ್ ಆ್ಯಡ್ ಮಾಡ್ತೀರಾ ಅಂದ್ಕೊಳ್ಳಿ. ನೀವು ಆ ಬೀಕರ್ನ ಅಡಿ ಅದರ ತಳನ ಟಚ್ ಮಾಡಿ ನೋಡಿ. ಓಕೆ, ಪೊಟ್ಯಾಷಿಯಂ ನೈಟ್ರೇಟ್ ತಗೊಂಡು some amount of water nalli add potassium nitrate and touch the lower part, touch the beaker. Okay, ಏನಾಗುತ್ತೆ? You will feel cold. You will feel cold. That means what? Heat is being absorbed in the reaction. That means potassium nitrate gets dissolved. That means solid enters solution phase, liquid phase when it is dissolved in water. For this process delta H is positive. Okay, the value is close to 34.89 kilojoule per mole. That means when we dissolve 1 mole of potassium nitrate in water, then this much amount of heat is absorbed. That means the forward reaction is endothermic in nature. Endothermic in nature. Okay. Second situation, same quantity of water. Instead of potassium nitrate, I add potassium hydroxide. Now if you touch at the bottom, you will feel heat, you will feel hot. Okay, ಅದು ಸ್ವಲ್ಪ ಹಾಟ್ ಆದ ಹಾಗೆ ನಮಗೆ ಪರ್ಸೆಪ್ಷನ್ ಬರುತ್ತೆ. ಯಾಕೆ ಹಾಗೆ ಬರುತ್ತೆ ಅಂತ ಕೇಳಿದ್ರೆ, ಪೊಟ್ಯಾಷಿಯಂ ಹೈಡ್ರಾಕ್ಸೈಡ್ ಸಾಲಿಡ್ ಫೇಸ್ when it is dissolved, that is if the solid is entering solution phase, then aqueous phase ಅಂತ ಬೇಕಾದರೆ ಹೇಳಬಹುದು. Better we will use the term aqueous phase. When from solid phase it is entering aqueous phase, then the amount of energy that is released is close to minus 57.6 kilojoule per mole. That is, when every 1 mole is dissolved, so much amount of energy is released. So this is an exothermic process. This is an exothermic process. So we are all well aware about endothermic and exothermic processes, alva. We have learned this in last year previously in thermodynamics and thermochemistry. Correct, alva? So endothermic process is a process in which energy is absorbed in the process. Exothermic nalli energy is released. Now, ಇವೆರಡೂ ಪ್ರಾಸೆಸ್ಗೆ ಎಫೆಕ್ಟ್ ಆಫ್ ಟೆಂಪರೇಚರ್ ಬೇರೆ ಬೇರೆ ಆಗಿರುತ್ತೆ. ಹೇಗೆ ಗೊತ್ತಾಗುತ್ತೆ? ವಾಟ್ ವಿಲ್ ಬಿ ದ ಎಫೆಕ್ಟ್ ಆಫ್ ಟೆಂಪರೇಚರ್ ಆನ್ ಸಾಲಿಬಿಲಿಟಿ? ಸೊ ವಿ ಕ್ಯಾನ್ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡ್ ದ ಎಫೆಕ್ಟ್ ಆಫ್ ಟೆಂಪರೇಚರ್ ಆನ್ ಸಾಲಿಬಿಲಿಟಿ ಫಾರ್ ಡಿಫರೆಂಟ್ ಪ್ರಾಸೆಸಸ್ ಬೇಸ್ಡ್ ಆನ್ ವಾಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಲೀ ಚಾರ್ಟ್ಲಿಯರ್ಸ್ ಪ್ರಿನ್ಸಿಪಲ್. ಈ ಲೀ ಚಾರ್ಟ್ಲಿಯರ್ಸ್ ಪ್ರಿನ್ಸಿಪಲ್ನೂ ಕೂಡ ನಾವು ಫಸ್ಟ್ PUC ನಲ್ಲಿ ವಿ ಹ್ಯಾವ್ ಸ್ಟಡಿಡ್ ಅಲ್ವಾ? We have studied Leach-Chatelet's principle in the chapter Chemical Equilibrium. A Leach-Chatelet's principle ಏನು ಹೇಳುತ್ತೆ? Whenever to a system at equilibrium, whenever we add a constraint, the equilibrium shifts in that direction where the effect of constraint is either reduced or it is totally nullified. ಕರೆಕ್ಟ್ ಅಲ್ವಾ? ಸೊ ಈಗ ನಮಗೆ ಇಲ್ಲಿ ಈಕ್ವಿಲಿಬ್ರಿಯಮ್ ಎಲ್ಲಿದೆ? ನಾವು ಆಗಲೇ ಡಿಸ್ಕಸ್ ಮಾಡಿದ ಹಾಗೆ ದೇರ್ ಆರ್ ಟೂ ಪ್ರಾಸೆಸಸ್. ಒನ್ ಈಸ್ ಡಿಸೊಲ್ಯೂಷನ್, ಸೆಕೆಂಡ್ ಈಸ್ crystallization. Both are taking place at equal rates. Therefore, there is equilibrium. So, therefore, any factor that is altering the equilibrium will lead to, will provoke the system to respond in such a manner that the effect of the altering factor is reduced or it is totally nullified. Okay. So, ಇಲ್ಲಿ ಏನಾಗ್ತಾ ಇದೆ? ಫಸ್ಟ್ ರಿಯಾಕ್ಷನ್ ತಗೊಳ್ಳೋಣ. ಫಸ್ಟ್ ಪ್ರಾಸೆಸ್ ಈಸ್ ಎಂಡೋಥರ್ಮಿಕ್ ಪ್ರಾಸೆಸ್. ಸೊ ಎಂಡೋಥರ್ಮಿಕ್ ಪ್ರಾಸೆಸ್ನಲ್ಲಿ ನಾವೇನಾದರೂ ಟೆಂಪರೇಚರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡಿದ್ರೆ ಯಾವ ರಿಯಾಕ್ಷನ್ ಫೇವರ್ ಆಗುತ್ತೆ? ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್ನ, ರಿವರ್ಸ್ ರಿಯಾಕ್ಷನ್? ನೋಡಿ, ಇಟ್ ಈಸ್ ವೆರಿ ಸಿಂಪಲ್. ನಾವು ಟೆಂಪರೇಚರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಅಂತಂದರೆ ಏನರ್ಥ? ವಿ ಆರ್ ಸಪ್ಲೈಯಿಂಗ್ ಮೋರ್ ಅಮೌಂಟ್ ಆಫ್ ಹೀಟ್. In forward reaction, heat is absorbed. Okay, heat is absorbed. So, ನಾವು ಹೀಟನ್ನು ಹೊರಗಡೆಯಿಂದ ಸಪ್ಲೈ ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಅಂತಂದರೆ ಏನಾಗಬೇಕು? ಹೊರಗಡೆಯಿಂದ ಸಪ್ಲೈ ಮಾಡಿದ ಹೀಟು ಅಬ್ಸಾರ್ಬ್ ಆಗಬೇಕು. ಯಾಕೆ? ಎಫೆಕ್ಟ್ ನಲ್ಲಿಫೈ ಆಗಬೇಕಲ್ಲ ಅಲ್ವಾ? ಸೊ ಹೀಟ್ ಈಸ್ ಸಪ್ಲೈಡ್, ಈಕ್ವಿಲಿಬ್ರಿಯಮ್ ಈಸ್ ಆಲ್ಟರ್ಡ್. ನೌ ದ ರಿಯಾಕ್ಷನ್ ಶುಡ್ ಶಿಫ್ಟ್ ಐದರ್ ಇನ್ ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್, either in forward direction or in reverse direction. So, which direction if the reaction shifts nullifies the effect of constraint, nullifies the effect of temperature? We are supplying heat. Okay? ಹೊರಗಡೆಯಿಂದ ಜಾಸ್ತಿ ಹೀಟ್ ಕೊಟ್ಟಿದ್ದೀವಿ. That heat should be absorbed so that the increase in heat, increase in temperature gets nullified. ಯಾವ ಪ್ರಾಸೆಸ್ನಲ್ಲಿ ಅಬ್ಸಾರ್ಬ್ ಆಗ್ತಾ ಇದೆ? ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನಲ್ಲಿ ಅಬ್ಸಾರ್ಬ್ ಆಗ್ತಾ ಇದೆ. So, for endothermic reaction, increase in temperature increases solubility. Alva? Decrease in temperature decreases solubility. Now, temperature ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ ಜಾಸ್ತಿ ನಾವು ಸೊಲ್ಯೂಟ್ನ ಆ್ಯಡ್ ಮಾಡಬಹುದು. ಓಕೆ, ಟೆಂಪ್ರೇಚರ್ನ ಕಡಿಮೆ ಮಾಡಿದ್ರೆ ಸೊಲ್ಯೂಟ್ನ ನಾವು ಕಮ್ಮಿ ಅಮೌಂಟ್ ನಾವು ಸೊಲ್ಯೂಟು ಆ್ಯಡ್ ಮಾಡ್ಬೋದು. ಎಕ್ಸೋಥರ್ಮಿಕ್ಗೆ ನೋಡಿ, ಎಕ್ಸೋಥರ್ಮಿಕ್ ಪ್ರಾಸೆಸ್, ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್, ಹೀಟ್ ಈಸ್ ಲಿಬರೇಟೆಡ್. ಓಕೆ, ನಾವು ಇಲ್ಲಿ ಕೂಡ ನಾವು ಹೀಟ್ ಕೊಟ್ಟು ಟೆಂಪ್ರೇಚರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಅಂತ ಅಂದ್ಕೊಳ್ಳೋಣ. ಓಕೆ, ನಾವು ಟೆಂಪ್ರೇಚರ್ ಇನ್ಕ್ರೀಸ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ ಅಂದರೆ ಹೀಟು ಸಪ್ಲೈ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. ಸೊ ಈಕ್ವಿಲಿಬ್ರಿಯಮ್ ಆಲ್ಟರ್ ಆಯಿತು. ಈಗ ಈ ಎಫೆಕ್ಟ್ ನಲ್ಲಿಫೈ ಆಗಬೇಕು, ಈ ಎಫೆಕ್ಟ್ ರೆಡ್ಯೂಸ್ ಆಗಬೇಕು. ಹೇಗಾಗುತ್ತೆ? ವಿ ಆರ್ ಸಪ್ಲೈಯಿಂಗ್ ಹೀಟ್ ಫ್ರಮ್ ಔಟ್ಸೈಡ್, ದ್ಯಾಟ್ ಹೀಟ್ ಶುಡ್ ಬಿ ಅಬ್ಸಾರ್ಬ್ಡ್ ಸೊ ದ್ಯಾಟ್ ದ ಎಫೆಕ್ಟ್ ಈಸ್ ನಲ್ಲಿಫೈಡ್ ಅಲ್ವಾ? ಸೊ ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್ನಲ್ಲಿ ಫಸ್ಟ್ ಆಫ್ ಆಲ್ ಹೀಟ್ ರಿಲೀಸ್ ಆಗ್ತಾ ಇದೆ, ನಾವು ಇನ್ನೊಂದು ಸ್ವಲ್ಪ ಹೀಟ್ ಹೊರಗಡೆಯಿಂದ ಕೊಡ್ತಾ ಇದ್ದೀವಿ. ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್ ಫೇವರ್ ಆದರೆ ಇನ್ನೊಂದಷ್ಟು ಹೀಟ್ ಬರುತ್ತೆ. ಸೊ ಫಾರ್ವರ್ಡ್ ರಿಯಾಕ್ಷನ್ ಫೇವರ್ ಆಗೋದಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ, ಬಿಕಾಸ್ ದ ಎಫೆಕ್ಟ್ ವಿಲ್ ನಾಟ್ ಬಿ ನಲ್ಲಿಫೈಡ್. ಸೊ ಏನಾಗುತ್ತೆ? Definitely, if you supply heat, if you increase temperature by supplying heat for an exothermic reaction, reverse reaction will be favorable because the supplied heat should be absorbed in order to nullify the effect of increase in temperature. So, for an exothermic reaction, increase in temperature decreases solubility. Okay, increase in temperature decreases solubility. ಅಂದರೆ ನಾವು ಜಾಸ್ತಿ ಟೆಂಪ್ರೇಚರ್ ರೈಸ್ ಮಾಡಿದಂಗೆಲ್ಲ ಸಾಲ್ಯುಬಿಲಿಟಿ ಕಡಿಮೆ ಆಗ್ತಾ ಬರುತ್ತೆ. ನಾವು ಕೋಲ್ಡ್ ಕಂಡೀಷನ್ನಲ್ಲಿ ಜಾಸ್ತಿ ಸಾಲ್ಟ್ನ ಡಿಸಾಲ್ವ್ ಮಾಡ್ಬೋದು, ಹಾಟ್ ಕಂಡೀಷನ್ನಲ್ಲಿ ಕಡಿಮೆ ಸಾಲ್ಟ್ನ ಡಿಸಾಲ್ವ್ ಮಾಡ್ಬೋದು. So this is the effect of temperature on solubility. Okay. Then we have the effect of pressure. Third factor is pressure. Okay. We are discussing about solid in liquid kind of solute. Okay. So solid in liquid kind of solute ge effect of pressure is not that much considerable. Okay. Change in pressure does not affect solubility to a very great extent. Okay. That is not considerable at all. Yake antandre, see, solid is solute, solute is solid, liquid is solvent, solvent is in liquid phase. So these are the compressibility for solid and liquid is very less. Alva? They are not highly compressible, unlike gases. Gases are highly compressible, but solid and liquid are not so compressible. Adike the volume of there is hardly any difference in the volume of solid or liquid when we change pressure. Therefore, the effect of pressure is almost we can say there is no effect. If we alter pressure, there is no effect on solubility. Okay. Now this is about the factors determining solubility for solid in liquid kind of solution, where we have understood the effect of nature of solute, then the effect of temperature and the effect of pressure. Now after this, let us consider gas in liquid kind of solute. Liquid in liquid we will take up later. Okay. We are discussing about liquid phase solutions. Liquid phase solution where solvent is liquid. Now so far we discussed about the effect of the factors affecting solubility for solid in liquid kind of solution. Now we will discuss about, now let us consider gas in liquid kind of solution. That means solute is gas, solvent is liquid. Okay. Now factors affecting solubility. Just like what we discussed previously, we will again consider different factors and we will discuss the role. ಆ ಫ್ಯಾಕ್ಟರ್ನ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ, ಕಮ್ಮಿ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ. ಓಕೆ. ಫ್ಯಾಕ್ಟರ್ಸ್ affecting factors that determine solubility. Factors that determine solubility. First, as usual, it is nature of solute and solvent. Nature of solute. Here also the same principle holds true. Like dissolves in like. For example, polar solutes such as carbon dioxide, okay, ammonia, HCl, these are all polar. They are highly polar because see, there are atoms with great difference in electronegativities. Carbon and oxygen, oxygen is more electronegative. Nitrogen and hydrogen, nitrogen is more electronegative. Hydrogen and chlorine, chlorine is more electronegative. So because of the difference in electronegativities, there is charge separation in the molecule. Therefore, there is polarity. Therefore, these molecules are considered to be polar, and they can very much interact if the solvent is polar, such as water. Water has polarity because oxygen has greater electronegativity than hydrogen. Okay. Therefore, these are soluble in water. Okay. But if we consider non-polar solutes such as non-polar gases such as oxygen, nitrogen, etc., methane, these are non-polar. They are not soluble in water. Instead, they might be soluble. They are in fact soluble in these are non-polar. They are soluble in solvents such as say for example cyclohexane, or it could be diphenyl, benzene, etc. because these are non-polar. Okay. So the idea of like getting dissolved in like holds true for gas in liquid kind of solution also. Now let us move on and discuss the effect of temperature. How does temperature affect solubility of a gaseous solute in liquid solvent? Usually the solubility of all gases generally decreases with increase in temperature. Solubility decreases with increase in temperature. Solubility decreases with increase in temperature. This holds true for almost all gases. The reason is, there are basically two reasons. First reason is, most of them are exothermic reactions. As we discussed previously, if the reaction is exothermic, then if you supply heat, okay, then that heat has to be absorbed, okay, so that the effect of increase in heat will be nullified. So if the forward reaction, that is dissolves and enters solution phase, so this is liquid or solute in solution phase, okay. So this reaction generally it is an exothermic reaction. Certain amount of heat is liberated. So if that is the case, if we increase temperature, then reverse reaction will be favored, because if the forward reaction is exothermic, then the reverse reaction will be definitely endothermic in nature. Okay. This is one reason. Second reason is, increase in temperature, increases kinetic energy of gas molecules. Okay. This we have studied in kinetic theory of gases. The kinetic energy of the gases is a function of absolute temperature, alva. So the gas molecules which are in solution phase, due to increase in their kinetic energy, they have a tendency to come out of the solution phase and enter into gaseous phase. So because of these two reasons, generally increase in temperature decreases the solubility of gases in liquids. So that is why aquatic animals, aquatic life, they are more comfortable in cold environment, in cold season, because more and more the solubility of oxygen in water will be more. So if there is more oxygen in water, they have access to more oxygen, and the organism can be comfortable because there is more oxygen. But in hot weathers, they are not quite comfortable. So this is the effect of temperature on the solubility of a gas in liquid. Now coming to the most important aspect, most important feature in this chapter, that is effect of pressure on the solubility of gas in a liquid. So generally we say effect of pressure. So increase in pressure increases the solubility. This is the general statement. increase in pressure increases solubility. For example, let us consider a solution in which certain gaseous solute is dissolved, in which a certain gaseous solute is present above the solution and certain solute particles are present inside the solute phase. So, certain particles, certain gas molecules are trying to enter the solution phase and certain others are trying to enter the gaseous phase. So, these particles, gaseous particles, they have pressure, what we call it as partial pressure of that gas. Now, say for example, the entire container is fitted with a piston. Now, I am adding weights to this piston. I am adding weights to the piston and increasing the pressure. If I add weights here, that will increase the pressure. So, when the pressure increases, more and more solute particles enter the solution phase. Thereby increasing the solubility of the gas. So, solubility of a gas increases with increase in pressure. This relation we call it as Henry's law. So, we can state Henry's law as follows. The solubility of a gas is directly proportional to the partial pressure of the gas above the liquid, above the solution. The solubility of a gas at a particular temperature is directly proportional to the partial pressure of the gas that is present above the solution. Say for example, if P is the partial pressure measured in atmosphere or usually measured in bar, then X is mole fraction. If X is solubility measured in mole fraction, this represents solubility. Then we can say that partial pressure of a gas is directly proportional to mole fraction of the gaseous solute dissolved in the solution. Okay? Partial pressure of the gas is directly proportional to the mole fraction. So, this is another way of expressing Henry's law. So, we can equate this, we can take out the symbol of proportionality and equate this and we get constant. Yeah, if we take out constant for proportionality symbol, we can write this as P is equal to Kh into X, where P is partial pressure measured in bar and Kh is Henry's constant and X is mole fraction. The unit for Henry's constant will be usually will have the same unit as the unit for partial pressure, that is bar or kilobar or atmosphere. Okay? Now, so mole fraction or solubility can be written as the fraction of P into Kh. This is this has a different value. This has different value for different gases. So, what does this represent? The greater value of Kh, if a gas has greater value for Kh, then that means it requires more pressure to dissolve a certain amount of gas. Greater value of Kh represents more pressure is required to dissolve a certain amount of gas. Smaller value of Kh represents a small amount of pressure is enough to solubilize certain amount of gas. So, we can understand this using an example. Kh for oxygen and KH for carbon dioxide at 20 degrees Celsius is as follows. So for oxygen it is close to 47 kilobar, and for carbon dioxide it is 1.67 kilobar. That means among oxygen and carbon dioxide, which is more soluble at a particular temperature? Definitely the one with lower value of KH, lower value of KH. These, what I have written here, represents the values of KH in kilobar. Okay? Carbon dioxide is more soluble in water than oxygen at a given temperature. And coming to this, this represents, this is just like an equation, y is equal to mx, but c is equal to 0. What does that represent? We can obtain a straight line by plotting partial pressure on y axis, partial pressure on y axis, then mole fraction on x axis, partial pressure on y axis and mole fraction on x axis. Since c is equal to 0, we get a straight line passing through origin. We get a straight line passing through origin, and by obtaining the slope we can obtain the value of KH. So this is about Henry's law and its mathematical form. Now let us understand certain applications of Henry's law. Let us understand about certain applications of Henry's law. So where do we get to use Henry's law? Applications of Henry's law. The very first application is, we have heard about soda water, or we have heard about carbonated beverages. Carbonated beverages. Soft drinks such as, we have heard about soft drinks of several brands such as Coca-Cola, Pepsi, etc. So when those soft beverages are manufactured, they are manufactured under a very high pressure. That is why it is done so. It is because the carbon dioxide, more and more carbon dioxide should get dissolved, so that will add for the taste of the beverage. So as soon as you open the bottle, more extra pressure decreases. As soon as you open the bottle, pressure decreases. The extra carbon dioxide that was dissolved will come out. Okay? So this is one place where we find application of Henry's law. Second application is, people living in high altitude, or people who go for climbing, who go for mountaineering, ದೊಡ್ಡ ದೊಡ್ಡ ಬೆಟ್ಟಗಳನ್ನು ಹತ್ತರಲ್ವಾ, Mount Everest, etc. So at high altitude, the partial pressure of oxygen is less. Therefore, less oxygen gets dissolved in the blood. Okay? So the solubility of oxygen in the blood becomes less, gets reduced, and that leads to a condition called anoxia. So the people suffering from anoxia, they don't have clear vision and they can't think properly. It leads to such a condition. Okay. Then third application is scuba divers. Scuba divers. See, these people who are go inside the sea, who dive inside the sea. Okay, they carry oxygen for breathing. So as soon as they come out at the lower regions, when they penetrate inside the sea, when they get submerged at the lower regions, the pressure is very high. So therefore, the gas that they are breathing in, the partial pressure is also more, therefore more and more gas gets dissolved. Okay. So when they suddenly come out, these gases such as nitrogen, oxygen, etc., they come out of blood vessels rapidly, very rapidly. Those gases come out of all these blood vessels. That can lead to a medical condition called bends. That can lead to a condition called bends that can cause acute pain locally. Okay, ಯಾವುದೆಲ್ಲ ರೀಜನ್ ನಲ್ಲಿ ಈ ತರ ಬೆಂಡ್ಸ್ ಫಾರ್ಮೇಷನ್ ಆಗ್ತಾ ಇದೆ ಅಲ್ಲೆಲ್ಲ ತುಂಬಾ ನೋವು ಅನುಭವಿಸುವಂತಹ ಪರಿಸ್ಥಿತಿ ಬರಬಹುದು. So for that reason, what they do, they mix their gas, the gas that they carry in the cylinder, with certain other gas such as helium. Okay, they mix their gas with certain other gas such as helium that decreases the partial pressure of nitrogen and oxygen, thereby decreasing the solubility. Therefore, when they come out, the effect of bend is not observed. So these are certain applications. These are certain applications of Henry's law. So this is an important question that can be expected from the exam perspective. State Henry's law, its mathematical expression, and the applications of Henry's law. Now let us take up a couple of numerical problems based on Henry's law. The problem is as follows. Okay. If nitrogen gas is bubbled through water at 293 Kelvin, how many millimoles of nitrogen gas would dissolve in 1 liter of water? How many millimoles of nitrogen gas would dissolve in 1 liter of water? Assume that nitrogen exerts a partial pressure of 0.987 bar. Assume that nitrogen exerts a partial pressure of 0.987 bar. Given that Henry's law constant for nitrogen at 293 Kelvin, is 76.48 kilobar. 76.48 kilobar. Now, nitrogen gas is bubbled in water at 293 Kelvin. Now the partial pressure, at a partial pressure of 0.987 bar, and the Henry's law constant is also given to be 76.48 kilobar. Now what we have to do is, we have to find out how many millimoles of nitrogen is dissolved in the solution. Okay, so we can start. This is the first problem on Henry's law. Okay, as usual, we shall take down what is given in the problem. What is given? We have the partial pressure of nitrogen. Partial pressure of nitrogen is 0.987 kilobar. Then we have Henry's law constant 76.48. Henry's law constant 76.48 kilobar. I think this is not the first quantity, is just bar, not kilobar. Okay. Then we have to find out how many millimoles of nitrogen are dissolved. So for this, we shall first find out the solubility by applying Henry's law. That means we get the number of we get mole fraction. Okay. So according to Henry's law, we have partial pressure is equal to Henry's constant into mole fraction. Okay, so we can directly find out mole fraction of nitrogen by 987 divided by 76.48 into 10 to the power 3. Okay, if we simplify this, we get 1.29 into 10 to the power minus 5. This happens to be the mole fraction of nitrogen. But in the question, it is asked that we have to find out the number of millimoles of nitrogen dissolved. Now, what is the formula for mole fraction? Mole fraction of nitrogen is equal to number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of water. Mole fraction is the ratio between the number of moles of a particular component to the total number of moles of all the components present in the mixture. Okay. Now, the quantity that is present in the denominator, number of moles of nitrogen plus number of moles of water. Number of moles of nitrogen is so small compared to number of moles of water, is very small compared to number of moles of water. Therefore, this we can approximately assume it to be number of moles of water. Therefore, our equation for mole fraction of nitrogen reduces to number of moles of nitrogen divided by number of moles of water alone. It is as good as dividing this quantity with this instead of taking the total number of moles. Okay. Now, what is the number of moles of water? How do we get the number of moles of water? So, if the quantity of water is 1000 grams, because mass of 1 liter of water, mass of 1 liter of water, okay, mass of 1 liter of water divided by molar mass of water, molar mass of water. Since the density of water is 1 gram per ml, mass of 1 liter of water is considered as 1000 grams. Okay. So, molar mass is 18 as we know. So, this comes up to 55.55 moles. Okay. Now, this quantity we can substitute in the expression that we got for mole fraction. So, mole fraction of nitrogen is equal to we have already found out mole fraction of nitrogen, number of moles of nitrogen divided by number of moles of water. So, we need number of moles of nitrogen. Mole fraction of nitrogen is 1.29 into 10 to the power minus 5 into number of moles of water 55.55. So, this quantity when we multiply, it comes close to 71.66 into 10 to the power minus 5 moles. But in the question, we are asked to express in terms of millimoles. So, this becomes 0.7166 into 10 to the power minus 3 moles, moving 2 decimal points, or 10 to the power minus 3 is milli, 0.7166 millimoles. That is the answer that we have. Yeah, one more problem on Henry's law. Henry's law constant for carbon dioxide in water is, Henry's law constant for carbon dioxide in water is 1.67 into 10 to the power 8 Pascal at 298 Kelvin. 1.67 into 10 to the power 8 Pascal at 298 Kelvin. Calculate the quantity of carbon dioxide in calculate the quantity of carbon dioxide in 500 ml of soda water, 500 ml of soda water when packed under 2.5 atmosphere carbon dioxide pressure, when packed under 2.5 atmosphere carbon dioxide pressure at 298 Kelvin, at 298 Kelvin. This is similar to the problem that we have solved just now. So this is second problem on Henry's law. Now let us, as usually, write down what is given in the problem. The Henry's law constant for carbon dioxide is given to be Kh is equal to 1.67 into 10 to the power 8 Pascal. into 10 to the power 8 Pascal. Temperature is 298. Then we have to find out the quantity of carbon dioxide dissolved in 500 ml. So total volume of the solution will be 500 ml. Then partial pressure of carbon dioxide is 2.5 atmosphere. Partial pressure of carbon dioxide is 2.5 atmosphere. Now again we shall apply Henry's law. Henry's law equation, P is equal to Kh into mole fraction of carbon dioxide. So we can find out mole fraction of carbon dioxide by substituting the values. 1.67 into 10 to the power 8, 2.5 atmosphere, 2.5 atmosphere. We have to express atmosphere in terms of Pascal. We can express atmosphere 2.5 atmosphere into 101.3 kilopascal. The 1 atmosphere is 101.3 kilopascal, or to be more precise 101.325. Okay, 1 Pascal is 101.3 kilopascal. So therefore 2.5 Pascal will be 2.5 atmosphere will be 2.5 into 101.325 Pascal divided by 1.67 into 10 to the power 8. So that we have uniformity in the units that we are using. We cannot consider numerator in terms of atmosphere and denominator in terms of Pascal. So ಒಂದೊಂದು ಯೂನಿಟ್ ಅಲ್ಲಿ ನಾವು ಯೂಶುವಲಿ ನಾವು ಯಾವಾಗಲೂ ಕೂಡ ಯೂಸ್ ಮಾಡಲ್ಲ. ಎರಡೂ ಕೂಡ ಯೂನಿಟ್ಸ್ ನಲ್ಲಿ ಯೂನಿಫಾರ್ಮಿಟಿ ಇರಬೇಕು. ಅದಕ್ಕೆ ನಾವು 2.5 ಅಟ್ಮಾಸ್ಫಿಯರ್ ಅನ್ನೋದನ್ನ ಪಾಸ್ಕಲ್ಗೆ ಕನ್ವರ್ಟ್ ಮಾಡ್ಕೊಂಡಿದ್ದೀವಿ. Okay, so if we simplify this, then the value that we are getting is 1.517 into 10 to the power minus 3. 1.517 into 10 to the power minus 3. What is the unit for this? This doesn't has any unit because it is mole fraction. Number of moles in the numerator, number of moles in the denominator. Therefore, no unit. Okay. Now, this is mole fraction. In the question it is asked that what is the amount of carbon dioxide dissolved? That means we have to find out mass in grams. Okay. For that we will first find out number of moles of carbon dioxide, then we can find out mass of carbon dioxide in grams. This is the expression of mole fraction of carbon dioxide, ratio between number of moles of carbon dioxide to the total number of all the components present in the solution. So again, like previous problem, we can consider that the quantity number of moles of carbon dioxide is way far less than the quantity number of moles of water, because always in a solution the amount of solute is very less. Now, so what we can write, the total number of moles of carbon dioxide and water can be approximately expressed as number of moles of water. So if we divide this quantity by this whole quantity, it is as good as dividing this quantity with the number of moles of water alone. Therefore, number of moles of carbon dioxide becomes, mole fraction of carbon dioxide becomes number of moles of carbon dioxide divided by number of moles of water. Okay. Now, number of moles of water is how much? We have to consider weight of water. In the question, it is asked that we have to find out the number of moles of, the amount of carbon dioxide that is dissolved in 500 ml of the solution. Okay. So, if we consider this to be 500 ml, the weight of water will be 500 grams. The weight of water will be 500 grams, assuming the density of the solution to be 1 gram per ml. Therefore, the number of moles of water can be the mass of water, mass of solution, mass of solvent water divided by molar mass of water. Molar mass of water. Mass of water is how much? 500 grams, because we have taken 500 ml of the solution, divided by molar mass is as usual 18. So, we get 27.78 moles. By substituting this here, number of moles of carbon dioxide we need, mole fraction of carbon dioxide is 1.517 into 10 to the power minus 3 into 27.78. So, this will come close to 42.14 into 10 to the power minus 3, 42.14 into 10 to the power minus 3 moles. From this we can find out the amount of carbon dioxide dissolved in terms of grams. Okay. If we want to convert number of moles into weight in grams, then we multiply number of moles with the molar mass. It is just like what we have here. Number of moles is mass by molar mass. If we want mass, we can multiply number of moles with molar mass, so that we get number of grams. So, amount of carbon dioxide is equal to number of moles of carbon dioxide, multiplied by molar mass of carbon dioxide. Number of moles we have got 42.14 into 10 to the power minus 3, molar mass is 44 gram per mole. So, now if we multiply this, the answer that we get is 1.854 grams. So, these are certain numerical problems that we have solved on Henry's law. Hope you have understood the concept of solubility, then different factors that influence solubility for a solution of solid in liquid and for a solution of gas in liquid. And we have also learnt about Henry's law, its applications and certain numerical problems. In the next video class, let us discuss about solubility in a solution which is made up of a liquid solute and a liquid solvent. Thanks for watching. Thank you.